Maria, thank you very much. It's a great honor to be here because I have do have a long relationship with the Lasker Foundation and with Scripps. And I was privileged to actually meet Mary Lasker while she was living. And one of the things that Mary Lasker had always thought about was that these wonderful awards should not just be given, but they should be given in some sense of opulence. And they're always held at a luncheon at the Pierre Hotel in New York, which has to do with bestowing on them, in my opinion, a beauty and elegance which exceeds just the monetary award as well as the honor. And also, I don't know how Scripps manages to do it, but to get a second research facility in a nice place in the sun is an astounding achievement. And I commend the people who were able to do that, because surely the people that work here are more inspired perhaps than those who work on the snowy streets of Boston, but maybe not. I'm not sure. Also, in my capacity as a science reporter, I get to report on complex things in about 1:50 seconds. If I'm that's on a good day. Sometimes it's 1:40, sometimes it's even 1:30. And for people who aren't familiar with that, that's about 200 or 300 words of writing, including the things of the sound bites of the people that are covered. So I just want to make that sort of to inspire the two of you, because a lot of you were not here for the earlier presentation. And what I'd like to do is ask each of these scientists, and by the way, this program was put together very purposefully to have a distinguished scientist who's still working very well but has won the Nobel Prize, and a young assistant professor who's just beginning a brilliant career, and to sort of see the difference in how they speak and approach things, but just also the similarities. And that was part of today's program. And I think we want to pick up a bit on that theme as well in terms of how the sociology of science and how it works. But I would like each of you, starting with Jack, to give a 2 to 5 minute summary of what you said earlier today. Jack.
Okay, well, let me start off by thanking Jerry and Harry for providing a nice sunny place to come and escape this snowy or rainy streets of Boston. All right, I don't know if I can talk for less than an hour, but I'll try.
Yes, you can.
So just to summarize sort of what I talked about earlier and what we've been working on the last several years, we're essentially trying to create simple living systems from off-the-shelf chemicals. We want to understand how relatively simple molecules get together, self-assemble into more complicated structures, and start acting like biological systems, which means we want to see the emergence of Darwinian evolution from relatively simple chemical systems. So we do that by trying to build systems like that, simple cells. We're working on 2 components, the cell membrane, and we think we have a pretty good handle on how that part works, how we make them, how they can grow and divide. But for Darwinian evolution, you also need genetic material so that you can code for information, pass it on to future generations. And so that means we need a chemical process for the replication of nucleic acids, and that's a huge challenge. I think we've made some progress on that, but we have a long way to go. And then the idea is to try to put these 2 systems together and see if we can watch that combined system spontaneously evolve new functions that will make it gradually more efficient. And I think if we can do all of that, we'll have a synthetic biology, but also along the way, we get clues as to how life might have started on the early Earth.
Good. Very good. Ryan?
I've been practicing for the Ig Nobels. I did this in 7 words or less, I think. I'll do my best. So Jerry alluded to earlier the fact that this quote by Feynman about creating and understanding, and one thing that's prominent on this campus here at Scripps, Florida, and in La Jolla is our tremendous synthetic capabilities. And a lot of the synthetic chemists here will recognize Waller's synthesis of urea as the ushering in of the modern age of chemistry, where we don't look at molecules as being special and only being able to be produced by biology or to be harvested from the sea, but that we have these complex rules of how we put together molecules to put together atoms to create complex molecules that are potential drugs. And we enjoy that in chemistry, and we don't enjoy that level of control and understanding in biology. And my talk today centered largely on this idea of using microfluidics, which is the technology born out of the semiconductor fabrication, the semiconductor industry and the computer revolution in the 80s, but applying those principles to biology and chemistry, where we can make these devices that are intricate networks of channels and reactors and valves, not transistors and wires, to be able to present reagents in very controlled, reproducible ways. So that's very important, to be taking our reactions and porting them to other laboratories where people can look at our results. And the end result of this kind of control allows us to approach in a very synthetic way the assembly of very complex structures like cell membranes, vesicles, droplets, all of these kind of what are right now very complex and very uncontrolled processes. We can actually we can do reproducibly. We can actually reproduce mixing, which is a fundamentally chaotic process. We can do that using microfluidics. And so the idea is that these constructs that we can control and make have numerous applications. We talked about a couple of them in the lecture, and doing in vitro evolution and compartments to scaling up to making artificial cells and beginning to echo some of the themes that Jack raised in his talk.
Great. So what are we going to do now? I'm going to ask a few questions, but very few. And I really want to make this participatory exercise here, where everybody in the audience who would be comfortable to ask a question feels like it. And I also am going to call specifically on some teachers and students who submitted some questions in advance. But I want to start with a question for Jack. At the beginning of your talk today, you briefly mentioned the idea that you were looking at a kind of life that we're familiar with. And you can't even begin to think of other kinds of life that may not be based on DNA and RNA and water, especially water, because we know there are, you mentioned, there are lakes of methane on other planets. And my question is a very simple one. What is life? And how do we know that there isn't already life with us here on Earth of a different kind that we don't even understand?
Okay, so I really don't like getting bogged down in definitions. I mean, we know biology when we see it. We want to make things that behave like biology. But I think Jerry Joyce has the most durable and relevant definition of life, which is a self-sustaining chemical system capable of Darwinian evolution. And I think for our purposes, that's fine. That does it.
Ryan, would you agree with that?
You work for him. Laboratory.
Yeah. All right. So
he's also the dean of the faculty.
Yeah, right. He is. Yeah. So you both mentioned Darwinian evolution, and without getting into any of the squabbles in the Florida school districts or the Texas craziness, but why? What do you mean by Darwinian when you talk about Darwinian evolution in your microglobules?
Microglobules.
What are you?
Darwinian evolution is the selective passaging of hereditary material from one generation to the next.
Now, is it necessary